Oh, thank you, Piers. I've actually sat where you are many times, but this is the first time in this lecture theatre I've been standing out the front here, so that's a first. That's good. So the subject of my talk tonight is at the interface between quantum computing and machine learning generally, which is not necessarily quantum. But what I will show you, I hope, is that quantum computing really should be thought of in the context of very powerful machine learning protocols. So let's begin. Oh, okay. Now, the first thing I want to say is there's nothing particularly new about learning machines. The world is full of learning machines and has been for, well, probably billions of years. These are biological learning machines. They're certainly not running on little silicon chips anywhere. And this is one of the simplest ones. It's a worm, C. elegans, which is, one of the workhorse specimens for biology, molecular biology, and various other aspects of biology. It's very small, only lives for 3 days. It has 900 cells, of which about a third are neurons. So clearly, its central nervous system is pretty important for its survival. So let's take a look at what it can do. First of all, it has sensors, it has sensation, it has neurons that can detect changes in the environment. And in fact, even if the environment isn't changing, it can move around and thereby change what its sensors are being exposed to. And it can act on the world because it has a motor neurons in its very small brain. It definitely exhibits goal-directed behavior, and it can, in fact, be taught elementary things like avoid nasty chemicals in the soup or predators and so on. So even it only has 900 neurons, it's actually quite a sophisticated learning machine. Of course, nobody engineered it. It was built by the principles of evolution. A very great deal is known about this little critter. There's a picture of its central nervous system. It's been completely mapped out. The entire circuitry of its limited brain is extremely well understood, where its sensations are entering its processing units. Well, in fact, it probably shouldn't be thought of as a processing unit because everything is all together. Basically, it's very similar to what is in our heads, spiking neural networks. Here's another example of a learning machine, a much more recent one. This is Gemini Robotics. There's dozens and dozens of these companies now. I could have chosen any. But it has the same basic structure. It has sensors, vision in particular. It has actuators. It can move and can hold things if it wants to in its hands. And it has a processing unit which enables it to learn. It's certainly not a neural network. It's a CMOS chip of some sort, probably a CPU, maybe connected to a GPU online. But it has embodied reasoning. It can feel and sense the world, and its training enables it to react to what it sees in the world. And it can do long horizon planning. Probably C. elegans doesn't do a lot of long horizon planning. But as you move up the evolutionary chain, obviously you move to more complex central nervous systems that do. And being able to adapt your behavior on the basis of past experience is a key feature of learning. And certainly these simple robotics models exhibit that. They have a kind of world model. This is a term which is bandied around a lot these days in the artificial intelligence community. Basically, it means it knows something about the physics of the world. Not a lot, but of course it's getting better all the time. Here's another example. This is from a Chinese company which builds these things for students and universities and so on for demonstration. It again has all these components. It has an actuator, it has sensors, and it has a built-in learning machine, this time an NVIDIA GPU based on their Jetson small GPU computer. It runs in real time. It has a control loop, and it provides some idea of depth and visual locomotion. I'm pretty sure this one also has a feature called SLAM, which is spatial localization and mapping, which is something that's been around in robotics for quite a while. Basically, it solves the problem that if you know where you are, you can build a map, but you can't know where you are till you have the map. So you need some sort of iterative process to be able to do spatial localization and mapping as you move around and learn the world. So here's another example of a learning machine, which I'll be spending a fair bit of time talking about. There isn't really any good name for it yet. Agentic self-driving laboratory is about the closest I could come up with. We're all well aware, I suppose, by now that there are Waymo self-driving taxis moving around London. I don't know whether they're actually taking passengers yet. There's probably a fair bit to learn about London for a self-driving car. But these are self-driving laboratories. They are robotic in the sense that they can act on the world, or at least some small subset of it, which might simply involve mixing reagents together in a chemical reaction, or perhaps directing a laser to some material and then collecting the light with photodetectors. And here's a few examples. There's many, many more all the time. So Autolabs does autonomous chemistry experiments, and you can interact with this remotely through the cloud. Obviously, you will have to satisfy some security requirements in order to do that. Otherwise, they would lose control of what chemistry experiments are actually being done, which could be a bit dangerous. There's ones in polymer electronics, and there's one announced from Google DeepMind, which is intended to synthesize all sorts of interesting materials, by which, as far as I can tell, they mostly mean superconductors. But that's the kind of learning or self-driving laboratory that I'm particularly interested in tonight. Something that can learn, can act on the world, and the world can act back on it in such a way that it can develop a new model for what it sees in the world. So this is very different from an LLM, a large language model, which doesn't go out and learn about the world for itself. It has been trained on all of our experience with the world as it exists on the internet. So all the sort of detritus of human civilization is on the internet, some of it good, some of it not so good. And all of that has gone into training an LLM. It only knows about the world insofar as some human has experienced it and written about it. But these are very different. These are physical devices that act on the world, and the world acts on them, and they build models of what's happening. So let's think about how we actually do this ourselves. After all, we didn't learn the laws of physics by building self-driving laboratories. I could go back to any point, but let's go back to Galileo, because I think he was perhaps the first person to realize that you could learn something important about the world by artificially constraining parts of it. This particular picture is meant to be Galileo demonstrating balls rolling down an inclined plane to some king or prince. But you get the idea. Now, this would have been completely incomprehensible to Aristotle, say, who would not have regarded anything you could learn about the world by artificially constraining it as valuable. You should go out and look at what is actually happening, not sort of messing it and constraining it in some way. But it was Galileo's genius to see, no, that's exactly what you should do. So what is an experiment in its most basic form is that, again, you push on the world and the world pushes back. But this time you arrange the situation to limit the kind of actions that you can do and the kind of things that you see. And that is the notion of a controlled experiment. And what you learn, well, we call it the laws of physics, but I would call it a compressed description of our experience of the world in this particular setting. So, of course, classical physics arose in this way, the physics of Newton, Maxwell, and Einstein. But at the beginning of the last century, we discovered something else about the world just from pushing on it and watching how the world responded. So classical agents, such as ourselves, learn to control the classical world, but a quantum agent, which could be us, but I think it's unlikely, will learn to control the quantum world. Nonetheless, we as classical agents, learning agents, have learned something about the quantum world by pushing on it and watching what happens, and then backing out the correlations between what signals we send into the experiment and what signals we get back. So the quantum world was discovered at the beginning of the last century. Here's some of the famous names associated with its discovery: Heisenberg, Planck, Schrödinger, and Max Born. And initially, of course, it was a source of enormous confusion. In fact, to some extent, it still is. People are arguing about what it all means to this day. Not that it matters very much, because we know sufficiently detailed ways to use it to build technologies. Even if we want to argue about Schrödinger's cat over a beer at the pub, that's fine. We can still get on and build machines with the rules we've discovered from quantum physics. But it's kind of interesting that biological learning machines like us, that were built through billions of years of evolution to experience a world where quantum effects were not really very evident, by actually following Galileo's ideas of a controlled experiment to discover that the world is rather more interesting, if you like, certainly more complicated than it had otherwise first seemed. So what are the principles of quantum physics? I'm not going to give you any equations, or just a couple, like 1 + 1 = 2. It won't get much more sophisticated than that, I promise you. But the two key principles of quantum physics are very, very counterintuitive. And the first one is that the world is irreducibly random. That is, given complete knowledge of the state of a physical system, there's at least one measurement with random results. There's quite a deal of sophisticated mathematics lurking behind this simple statement, but some of you may have heard of the Heisenberg uncertainty principle. So let's put this in that setting. Now, if the world was irreducibly random, you might think, well, how can we do anything? How can we learn anything if that entire game is just a coin toss? Well, the reason is, the flip side to that says that given complete knowledge of the state of a physical system, there's at least one measurement for which the results are certain. And it's this strange way in which certainty and uncertainty cohere in the quantum world that enables us to build quantum technologies. The difficulty is figuring out ways to intervene and control the odds governing these principles. Anyway, moving on from the discovery of quantum physics and those simple principles, we've since learned to build all sorts of interesting technologies that exploit those two simple principles. And the first one, a high precision sensing of fields and forces, very precise sensors for magnetic fields for use in neuroscience. Building precise clocks is perhaps one of the most important and valuable quantum technologies. Oh, is everything okay? Okay, sorry, I'll just check. Another example of is secure communications with photons. The entire internet runs on pulses of light coursing down optical fibers. They eventually get converted back into electrons and then reconverted back into photons, and they go on their way. But we're now learning how to do it with truly quantum states of light. I'll say a little bit more about that in a minute. Secure communication with photons, and then computing known functions efficiently. So this is quantum computing. You have some known function, and I'll say a little bit more about this in a minute. But the other use of quantum computing is to learn unknown functions from data. Now, you might think, how can I build a machine to compute an unknown function? If I don't know the function, how do I compute it? Well, the point is, in a learning architecture, you have enough examples of the function. You have lots of examples of the inputs and the outputs, and you train the machine to generalize on the basis of what it's seen to probabilistically implement the function that you don't know but is hidden in the data. Why is that not working? Okay, so I'm going to take a little diversion on statistics here because I want to illustrate at least one simple principle of quantum physics, which doesn't need much mathematics and just uses basically no more sophisticated mathematics than you need to describe a double coin toss. So this is a very simple game. It's called 2-Up. If it's played with fair coins, it's pretty boring. But of course, it probably isn't played with fair coins in most circumstances. But the basic idea is you toss 2 coins and you bet on the outcomes. You bet on whether they both come up heads or tails, or whether they come up odds. So it's odds or even. So there are 2 coins, 4 possibilities. So you need 2 binary numbers to store the outcome. Let's suppose a head is called a 0 and a tail is called a 1. And so we need 2 binary numbers to store the results of that. And what we want to calculate is what's the probability for an odd and what's the probability for an even. So I'm assuming most of you here have already figured that out, but let's just step through it. So the first example is we use what I'm loosely calling Laplace's rule of insufficient reason, which says if you don't know any better, that is, if you trust the people tossing the coins, assume that all outcomes are equally likely. And as there are 4 outcomes, we should assign a probability of 1/4 to each outcome. And then we use a simple rule, which could have been attributed to many people. I'll attribute it to Bayes, which says that if 2 events are indistinguishable, add the probabilities for the 2 indistinguishable ways it could be achieved. So an odd can be achieved in 2 ways. It could be a tail head or a head tail, 0, 1, 1, 0. The probability of each of those is 1/4. So the probability of an odd is 1/4 plus 1/4, which is 1/2. Pretty straightforward. However, we're now going to do that exact same experiment, but with quantum particles, this time photons, little elementary excitations of light. So we're going to do an experiment with so-called single photon sources. This is not a laser. It doesn't produce a massive number of photons. It just produces little pulses of light which have 1 and only 1 photon per pulse. It's a highly unusual state of light, but you can now buy devices to make these sources, and you can buy counters which work just fine at that very low light intensity. And I'll describe some very important technologies at the end of the talk that make use of that. So the idea is we send these photons towards a semi-silvered mirror, and it'll either get reflected or get transmitted. If you had a big stream of laser light coming at this thing, the intensity would just be divided 50% reflected, 50% transmitted. But here we're doing it 1 photon at a time. And so it either goes to the top detector and gives a click, and we call that 0, or it goes to the horizontal detector and gives a click, and we call that 1. Now you might think, well, why can't the photon split? Well, the reason we don't believe the photon splits is because then each would have half the energy of the original one. And as Einstein pointed out many, many years ago, the energy of a photon is related to its color. And so if the energy changed, the color would change. And we know from spectroscopy that doesn't happen at beam splitters. So this is truly a coin toss. So let's look at a little experiment involving this. We're going to do a coin toss with a photon. So we have a source of our single photons directed down towards this mirror. It has a 50-50 chance of being reflected or transmitted. So if it's reflected, it's detected at the upper detector with certainty. And if it's transmitted, it's detected at the lower detector with certainty. And you just do it over and over and over again, and you discover that it's roughly 50-50. So you think, is this a coin toss? There's only 1 coin in this case, so I only need 1 bit of information to store the outcome. If it was a perfectly reflecting mirror, there's no surprise at which detector is going to go off, and I don't need any bits of information to store the outcome. It's only in this case where there's some uncertainty that I need to set aside at least 1 bit in the record to store the result of the experiment. So is that a bit? Well, let's try the double coin toss experiment now. Let's take the photon and toss it again. So it comes down to the first beam splitter, or it could just be 1 really long beam splitter, it doesn't really matter. And it can be reflected, and then we'll just force it to make another choice. So we just put a perfectly reflecting mirror in the top path and send it back towards an identical beam splitter. Likewise, it could have been transmitted at the first beam splitter, and then we force it to choose again. So the question is now, what is the probability that we get it at the upper detector and the probability that we get it at the down detector. So if you look at the paths through this device, if a photon was behaving like a respectable classical thing, it could be reflected and reflected, in which case it goes to the upper detector, or it could be transmitted and transmitted, in which case it also goes to the upper detector. Or it could be transmitted and reflected and go to the lower detector, or it could be reflected and transmitted and go to the lower detector. So there are four possible paths: 2 reflections, 2 transmissions, 1 reflection, 1 transmission, or 1 transmission and 1 reflection. And you think if that is behaving like a coin toss, each of those should be equally likely. And as you can't tell when you get a 1 at the upper detector or 1 at the bottom detector, whether they were 2 reflections or whether it was 2 transmissions. Sorry, I think I misspoke that originally. So those are indistinguishable. 2 reflections and 2 transmissions all go to the upper detector. And so you think, well, Laplace's rule of insufficient reason, I'll add them together, so it should be 50-50 again. And just staring at that, you think, okay, it's 50%. Now, I stress that you do this 1 photon at a time. You only ever get 1 click at one or the other detector. Actually, the detectors aren't that great. They miss a few, but let's assume they're really good. And so you either get a click at the top detector or you get a click at the bottom detector, and you never get anything else. That's all you get. So you just run this many, many times, press the button, send photons in, and sample the statistics. But this is the result of the experiment. You discover that in this case, the detection at the upper detector is certain. So what was formerly irreducible uncertainty at the first beam splitter, just forcing it to do it again has rendered it certain. And this is one of the simplest examples I know of where the quantum description of what's going on hides both irreducible uncertainty and certainty within the same quantum state. I haven't changed anything about the source. I've just changed the experiment that I do with it. So let me show you the rules as to how that comes about. They're actually quite simple. It turns out that in quantum physics, probabilities are not the primary objective of the theory. There's something at a deeper level, which we don't have a good name for. I call it probability amplitudes. But the point is, probability amplitudes don't have to be positive, because the only way to get a probability is to square it. And this was an idea discovered by Max Born, or proposed by Max Born. It's just plonked down on top of quantum mechanics. It's the only way we can extract measurable results from the theory. And people have been arguing about where it comes from ever since, but it works just fine. So if I tell you what the probability amplitude for an event is, you just square it and you can then take the probability. So this is an interesting comment I should make at this point. Quantum theory has 2 faces. In one aspect, it's a probability calculus that says, if I give you the probability amplitudes, this is how you manipulate them to predict what will happen in the experiment. But the other phase of quantum mechanics, which is really the quantum physics part, tells you how to calculate the probability amplitudes in the first place. And that depends on the detailed physics. In this particular example, we will use quantum electrodynamics in its quantum optical low energy approximation. If it was an electron in a semiconductor, we'd use the description of condensed matter physics to calculate the probability amplitudes. If it's some exotic field theory, we would calculate the probability amplitudes differently. So if I give you the probability amplitudes, you crank the handle and compute the probabilities, but getting the probability amplitudes in the first place is actually quite difficult. And we spend a lot of time training our students to do that in an undergraduate curriculum. Okay, so let's move on. So in this particular example, here's how the theory works. It says that an event can happen in 2 or more indistinguishable ways. Add the amplitudes first. So this is very much like the Bayes rule, which says if 2 events classically can happen in 2 indistinguishable ways, add the probabilities. But quantum mechanics says no, don't add the probabilities, add the probability amplitudes, and then square to get the probabilities. And it just so happens, I'm not going to show you, if you crank the handle of quantum electrodynamics, of the physics of light and the physics of dielectric surfaces, you'll discover that the probability amplitudes for reflection and transmission and reflection are half, but one of them comes in with a negative sign. So when you add them together, they completely cancel, and the probability to go to the down detector is identically 0 in this case. So that is very strange. but that is the core of why complete certainty and complete uncertainty can coexist in the same quantum state. And the whole business of quantum technology is learning how to control the probability amplitudes in some particular physical setting, like light, photons, or electrons in semiconductors. In essence, we're sort of pushing the levers down into the quantum world and steering the probability amplitudes around to exploit these strange rules to generate the odds that we want for some particular application. So that's what quantum technology is really all about. So while those simple experiments I just showed you with photons seem incredibly simple, they already give you enough basic physics to think about building photonic quantum computers. So the behavior of photons at beam splitters is one or two other rules you will need. So you won't be able to go out straight away and design a quantum computer on the basis of tonight's lecture, but you should think about it, definitely. PsiQuantum is one such company that by generating single photons, sending them through waveguides etched in various materials, silicon and what's the other one? Forgotten. Barium titanate, I think. Not sure. Mixing them together and then having very, very good single photon counters, you can work out how to do full quantum computation in that protocol, so long as when you count a photon, you can change something in the circuit that it traveled through. And by combination of measurement and feedback, you can do quantum computation. Here's the local one, Orca, developed by Ian Walmsley and his team. And they do pretty much the same sort of thing, not necessarily for universal quantum computing, but already it can do things which can't be simulated classically. So what is a computer, I guess? We should try and address this issue now. Everyone is so used to using them, they probably never really ask anymore what's in the box. But here's a picture from, I don't know if anybody saw the Netflix Three-Body Problem video or TV series, but in there, the basic story is that there's a civilization that lives in some unstable planetary system, which has got three bodies in universal gravitational motion, and this is a notoriously chaotic system. It's very hard to predict what's going to happen in such a system. And so they try anyway. So they decide to build a computer. And basically, the first thing they do is get a clock and put it on a tower. And I guess they beat a drum or something or flash a light. And every time the drum goes or the light goes, somebody, one of these soldiers down here holding a placard, which is black on one side and white on the other, looks to their left or their right. And depending on what they see, they turn it or don't turn it. And this is enough. This is basically a Turing machine to do computation, not a particularly efficient machine, but it illustrates the three features. You need a synchronized cascade of switches. That's what a classical computer is. Synchronized, so that in a sense the dominoes all fall in some nice sequence. They're conditional, whether one falls depends on whether something else was switched from 0 to 1, somewhere else in the circuit. And the switches have to be irreversible. It's extremely important. If you have a switch which bounces, it's completely useless. If every time you turn the light switch from on to off, it bounced, 30 or 40 times before it finally settled into one stable state, that would be very annoying. And so these switches have to be very dissipated. When they're switched, they go from on to off or off to on, and they stay there. Well, more or less. There's a little bit of noise in these circuits that you can't avoid. So now, this is how we think of a computer. We have some voltages which carry the clock signal, which I just think of as all voltages high, carrying 0, 0, 0, 0, 0. So that synchronizes everything. And then we have a whole bunch of binary strings coming in as time series. And these all run to a box such that all the binary numbers encoded in these voltages are turning switches on and off in a highly synchronized, cascaded array inside the box. But the thing I want to emphasize is this. It's this binary digits going in and binary digits coming out. What's in the box is pretty complicated, and people have got pretty good at coming up with things to put in the box to do this more and more efficiently. But essentially, it's a transformation on binary strings from input to output. By binary string, I just mean a long list of binary numbers. In fact, long lists of binary numbers in this case. So now I can show you what a quantum computer is. It looks like this. which is very similar, and this is important to understand. It is binary strings going in, voltages, photons, whatever you like, and it is binary signals coming out, physical signals, carrying the coding of 0 and 1. The trick with a quantum computer is what's in the box. So if we think of it as transforming binary signals into binary signals, what we put in the box are devices that operate on probability amplitudes to switch the fundamental units in the quantum computer from 0 to 1 and from 1 to 0. What's in the box can be incredibly energy efficient and not consume much energy, but obviously you put energy in to encode the input signal, and you get some of it back out again when you make the measurements. So a quantum computer is a machine for transforming strings of bits, just like a classical computer. In particular, it transformed probabilities of binary digits because quantum mechanics has this funny flavor of sometimes being deterministic and sometimes being random. So the best you can hope for is transform probability distributions over binary strings. And sometimes it can be pretty close to deterministic. And you do it by transforming probability amplitudes. And so computation in this picture is controlled interference of probability amplitudes. Think of lots of photons going through millions and millions of beam splitters where you can control all the reflectivities of the beam splitters in order to get the nice distribution out at the other end. And we know now that you can exploit the ability to control probability amplitudes to transform binary strings far more efficiently, that is with fewer steps or fewer clock cycles, than you could do classically. So you might think, well, why are we talking about probabilities and efficiency in the context of computation? Most people's view of computation is that's an entirely deterministic process, and it often is. But by now we know from machine learning that that is not a good way to think about computation. In the case of machine learning, we know that what's really going on in machine learning, they are deterministic algorithms, but they're trained on noisy data, and the machine adjusts as you run through it by feedback, as I'll describe in a minute. Efficiency just means how many time steps are required to finish the transformation of input to output. And we now know that a quantum computer can do this far more efficiently. So different algorithms have different scales. So if let's suppose n is the number of binary digits going in that specify the problem, if the number of steps goes as some power of the number of binary digits, we say that's efficient. But if it goes exponentially in the number of binary digits, we say that's hard. And so the algorithm, in this case, is going to depend upon the hardware that we actually use, whether it's classical or quantum. So here's an example of Shor's algorithm. I'll give a very simple statement of it. Peter Shor discovered in 93, 94, somewhere around then, of a very important algorithm, which doesn't sound important when I first tell you, but basically it says, if I multiply 13 times 19, they're prime numbers. I'm sure most of you could do that in your head, or at least with your phone, pretty quickly. But if I gave you 247 and said, what are the prime factors, it might take you a little longer to tell me that it's 13 and 19. If the number I gave you was the one underneath, it would take you quite a long time to tell me what the prime factors of that number are. You can sit there on your phone and just work through every prime number until you hit one that worked. So that doesn't scale very well. Every time I add another digit to that number, you need to do one more step. And so it's very bad. And there's, as far as we know, no good polynomial time classical algorithm for doing that, but quantum computers can do it very efficiently. They sometimes make mistakes because they're probabilistic, but you can easily check if the integers you get are right. You just multiply them together, which is very efficient. So this really put the cat among the pigeons, so to speak, when Peter Shor proposed this. And excuse me, at that time, various funding agencies around the world started putting a lot of money into quantum computing. No one had a clue whether you could do it or not, but it was a sufficient worry that they wanted to know if someone could do it in 50 years. 50 years is about the timeline that a security agency needs to be sure that secrets are indeed secret. But we now know we can do it. And in fact, the day in so-called Q day is the day in which this algorithm will break public key encryption, at least some of them that we use on the internet. So it turns out this difficulty of finding prime factors is used to secure transactions on the internet. It enables what's called public key cryptography. But if a quantum computer is built, those things would be vulnerable. And so now there's a big push underway to change all the security protocols on the internet from these kinds of things that can be broken by a quantum computer to new so-called post-quantum algorithms, which are invulnerable to quantum attack, or so we think. Now, we originally thought this was going to be, 30, 40 years away, but it's now pretty clear with recent progress in quantum computing that will be in the next 5 years, probably. So Google and all the banks and the UK government and so on have protocols in place to replace all of the encryption schemes, which is a big ask, it's going to be very expensive, all of the encryption schemes used in UK and business and banks and so on over to safe algorithms. Now, the problem is that already there are lots of hackers harvesting publicly available information which they can't decrypt in the hope that one day they will have a quantum computer and can decrypt it. In particular, there are lots of digital signatures that are lost and forgotten on the blockchain for Bitcoin that if you could harvest now, the minute you get a quantum computer, you could make a considerable amount of money from that data. Presumably by then, Bitcoin will have thought of some way to prevent this, but at the moment, it's a significant vulnerability. What else can we do with quantum computers that are probabilistic? Well, one thing we can do is financial modeling, and this is one of the key applications that we're interested in at NQCC. You might think, what has probabilistic computing got to do with financial modeling? Well, it turns out to be quite a lot, largely stemming from these three people, Scholes, Black, and Merton, who came up with the famous Black-Scholes equation, which is sometimes referred to as the equation that built Wall Street. It could equally well be referred to as the equation that led to the financial crisis in 2008, because it provided a supposedly simple algorithm for predicting the price of stock options, among other things. And basically it works like this. The number of buyers at any time is unknown. I know if I'm a buyer or a seller because I'm sitting at my computer typing away, but I don't have any idea what's going on elsewhere in everybody else's little office. But I can see the stock price, which somehow reflects, it's a measurement signal of all the buying and selling that's going on from all these individuals. And so if I can extract information from the stock price, assuming it hasn't been manipulated in any way, then can I predict whether a price will rise or fall, and perhaps try and make some money in the small fluctuations in the time it takes to act upon it. So the key is to estimate the number of buyers conditioned on the previous history of the price. And that's an incredibly random looking thing. It's called volatility. And it turns out that if I can look at the share price like this and compute the area under it very, very accurately, I have the beginnings of an algorithm to gain some small advantage in my actions in the market. It turns out that calculating the area under stochastic curves like that is very difficult, very time consuming. And of course, often there are thousands and thousands of shares that need to be computed, or financial instruments of one sort or another. But the best classical algorithms use Monte Carlo, which is basically just tossing coins. But a quantum algorithm uses these quantum coin tosses that I described earlier, and these are certainly faster, at least quadratically faster. It's not a massive exponential improvement like Shor, but when you're out there in the market, you don't have to be exponentially faster, you just have to be faster than everybody else, and you can make some money. And the reason is quantum probabilities are different. So these quantum amplitude estimation algorithms discovered by Locke Grover shortly after Shor's algorithm can be used in this setting, and there are other ways that we've learned to do it as well. In fact, just the sheer randomness is extremely useful for financial markets, and JP Morgan has its own quantum computing division where they're now certifying random numbers. They will give you a whole bunch of random, well, actually they won't give them to you. They will sell you a whole bunch of random numbers and certify that they are indeed random. There's not some sort of hidden pattern in there that somebody could exploit. At NQCC, we're doing work with HSBC and a quantum computing company, Rigetti, to use these sorts of stochastic simulations to detect fraud in financial transactions. In a financial transaction, let's suppose it's a credit card transaction, the information's pouring at you in real time. You haven't got a lot of time to make a decision. Most of the transactions are fine. There's a few anomalous ones which you have to catch, and you have to flag whether they are good or bad. And people get really annoyed if you tell them that their transaction was fraudulent when it wasn't. And so you don't want too many of those events popping up. But it turns out quantum, the way we can embed data in quantum computers is a good way for looking for anomalies like that. In fact, one of the other applications of this, looking for anomalies in large data sets, will be in the Large Hadron Collider at CERN, where there's these gazillion particles. They sort of bang protons together and particles fly out. Most of the time, it's sort of fairly predictable. Every now and then, some odd thing comes out, and they've got to catch it in petabytes of data. And one of the things I'm working with is the people at Rutherford Lab to develop quantum algorithms for looking for anomalous events very much more efficiently for LHC. Okay, let me finish by saying a little bit about machine learning now. So let me describe to you what I mean. I don't mean algorithmic machine learning. At the moment, the only machine learning most of us are familiar with are chatbots, which is just a bunch of binary digits crunching through a GPU. It's very similar to what I described before. But what I want to describe now is something a bit more like C. elegans. Imagine we have a farmer in the Cotswolds or somewhere, and they have some sheep and goats. And they're perhaps not a very good farmer, and they want to build an automatic sorting machine for sheep and goats because you don't want to send the sheep to the goat factory and vice versa. So they hire an engineer to build a machine with lots of pulleys and ramps and gates and all sorts of levers you can pull and push. And they start sending in the animals one by one, completely at random. And initially, they can come out in one of two channels. And initially, it's completely random. The sheep may come out in the G channel, or the goat may come out in the S channel, completely at random. But every time the engineer sees the wrong case, he pushes a lever or pulls a ramp up or tightens a spring or something like that to try and change the probability of the machine making a mistake. And you do this over and over and over and over again until you finally get to the point, having spent lots and lots of energy pushing against springs and levers and all the rest of it, where most of the goats come out in the goat channel and most of the sheep come out in the sheep channel. And now you're in business. You just, back up the relevant truck to the output and take them off to the, where they go, as you can imagine. So in this, what's happening is that this machine has now learned the difference between a sheep and a goat. I can't tell you where in that machine it has the difference between a sheep and a goat. I can't go in and say, that particular pulley there, that's the sheep pulley. It's the whole thing together is encoding what's going on. So the information is being compressed into a learned rule encoded in the physical hardware. So this means physical AI like this cannot be copied. One of the big problems we have most recently is open weight models, where they're just binary numbers sitting in a machine. Once I've trained it, I can copy all the binary numbers and give it to somebody else, and they can build the learning machine just fine. But in these machines, you cannot copy the numbers because they're not stored in memory. They're voltages and currents and magnetic fields and settings inside an actual physical piece of hardware. And that's pretty good. They go by various names, analog, neuromorphic. But they're also fundamentally more energy efficient. And this is why people are very, very interested in them. IBM have a project called Hermes, where they build these so-called analog neuromorphic chips, which learn in the way I've just described, a bit more than sheep and goats. And you can also do it with photonics. And one of the things that we're doing at NQCC is developing ways to do it, but with quantum rules instead of classical rules of electromagnetism. Just to give you a hint as to why quantum computers could be much more efficient, in a classical device, you can compute how much energy is dissipated as heat per training cycle. And it turns out to be proportional to the change in the error, change in the probability of making a mistake. So as the probability of error goes down, the energy dissipated goes down and down and down. It's roughly proportional to kT times the electronic charge. In the case of a quantum device, a photonic device, the temperature no longer matters. Planck's constant enters because it's a quantum device, and there's a new fundamental rate constant in there, which could be a spontaneous emission rate or a reflection probability through a beam splitter. And the fundamental energy dissipated per learning cycle for the quantum case can be substantially lower than it is for the classical case. So even without quantum advantage, quantum optical hardware machine learning will be more efficient than the classical case. But of course, we don't have to run it as a learning machine. We can run it as a straight bit sampling machine. And the UK is one of the world leaders in developing this technology. The National Quantum Strategy Mission requires that by 2035, in the UK, there will be a quantum computer capable of running 10 to the 12 operations and supporting applications that provide benefits in excess of anything that we do with a classical supercomputer. It's a bit of a stretch milestone, but I think it's very achievable. Of course, it's going to cost a lot of money, but it's going to make a lot of money for the UK economy as well. So we are well placed. So now let me just finish by making a connection between learning and quantum computers. So this is the picture I want to return to. We go back to Galileo, or more particularly the pioneers of quantum physics, who are intervening on the quantum world, but we automate it. We set up a quantum controller or quantum computer, which pushes on the world with, say, single photons, and it's pushing on a quantum world. It could be some very interesting material, like the sorts of things we've been discussing at the conference over the last couple of weeks. And the world responds by sending this stuff back to us, which we can then process in the quantum computer or the quantum controller. And of course, as I said before, we get out classical bits of information. Classical bits went into the quantum controller and classical bits come out. But now I can pass them to a classical machine learning device and automate the entire learning process. So this is a quantum automated laboratory. There are lots of things one could do with that. Here's one example that I'm particularly interested in. There are very interesting molecules called light harvesting molecules, which occur in photosynthesis in plants. They're one of the key steps to convert light into electrochemical energy. We could imagine putting those into an optical cavity, driving with single photon sources, but also pushing it with a classical laser, and then getting single photons out and running it through an Orca machine or a psi quantum machine. And what I've got here is a temporal convolutional network classical machine learning architecture. So that would be one way to learn new things about the world. Quantum photonic biosense is in fact a major industry around the world. One of my colleagues back in Australia has the center called Cubic, which does quantum light microscopy. There's lots of work done on silicon photonic ring resonators. It turns out the difference between a healthy cell and a sick cell can often be reflected in the refractive index of the cell. And so if you can probe that very quickly in real time using single photons, you can do better. Why would you want to use single photons? Well, the reason is that the photon budget has to be kept very, very low. Biological materials are easily destroyed. You could always do better just by cranking up the intensity, but then you kill it, or you blow it apart, or you fry it. And so really doing it with one and only one photon per pulse is the best thing you could do. And one of the things we're very interested in, this is a startup that I'm involved in called QDAR, is to do self-adaptive predictive sensing in exactly this setting of machine learning, quantum controller, physical world, and then come back up. And there's this whole predictive loop based purely on data coming from the real world. So with that, I will finish. I'll just point out that we're on the threshold of automated quantum discovery, that AI plus quantum computing can learn more about the world than humans ever could and learn it much faster. Will we understand it? Well, we don't actually understand what's going on in an LLM right now. It's even that's a hard problem, but this will be even harder because we won't be able to look inside the quantum computer. One thing you cannot do in a quantum computer is go in and measure what's going on, because that will wreck it. You can't even really interrogate what's going on, or at least not yet, the classical machine learning part, because that's the problem of interpretability. We're already struggling with that with LLMs, but now everything is coming from the real world. And the machine may itself discover new laws of physics that we're not aware of, but it will discover them in such a way that we can make use of it to build new materials and new technologies. And these technologies would then likely be beyond human understanding, which is a little bit disturbing, but what the hell? You can sell it and make a lot of money and improve people's lives. So with that, I'll finish. Thank you very much.
Yeah, go ahead. You have a good time? thing may have been microphone. No, no worries, I'll shout.
Okay. Yes. So there are two ways. All quantum computers use quantum entanglement. Quantum entanglement is a way of forcing correlations between events that are either much stronger or much weaker than you would otherwise expect. And quantum entanglement is one of the key aspects of building a quantum computer. We don't actually know which particular aspect of quantum entanglement, because when we build these devices, there'll be thousands or millions of qubits going in, all correlated in some very complicated way. But the other aspect in which quantum entanglement plays a key role is in quantum switches. So the sorts of quantum switches I'm interested in involve something called spontaneous emission, which means that a switch can go from on to off or off to on at zero temperature. And that is, in fact, a reflection of quantum entanglement between the state of the local switch and the state of its environment. So quantum entanglement enters in two key roles, in quantum machine learning and in regular quantum computing.
So one of the reasons that AI is being quite popular with some people is the effect that it's having on our environment. And I was wondering if you think that within the foreseeable future, analog, like computational methods, sort of like your model computing, for example, might allow us to have AI models that are efficient enough that we don't need to worry about the environment.
They will certainly be more efficient, but I wouldn't say that that will mean we don't have to worry about the environmental effects. Okay, so here's what will happen. I'm pretty sure this will happen. People will build analog neuromorphic physical so-called computing memory devices that will be 10 or 100 or maybe 1,000 times more efficient than GPUs. And you might think 10, 100, that doesn't sound like too much. But if I can divide my power bill by a 10 or 100, then I'm going to do very well. So you might think, okay, I can make a lot more money. So what will I do? Well, I'll just build more of those. And so now we're back to the same problem. We've got very, very efficient learning machines, but we're now just building even more of them. And so there still will have to be some careful consideration given to the policies involved in using the technology in an environmentally sound way. Oh, yeah. There are quite a few. In fact, I'm working with a PhD student at the University of Oxford, we're looking at developing quantum reinforcement learning for small little nano machines and nanobots. So the sorts of sensors I was describing before will be done with reinforcement learning. So there's a small but growing community interested in quantum reinforcement learning. To some extent, it's always been around. You can think of laser cooling as a kind of reinforcement learning. You take a gas of atoms and you apply laser pulses and you carefully change the frequency of the pulses based on the temperature of the gas till it's lower. That's a very elementary version. But yeah, absolutely, quantum reinforcement learning is a major discipline. Not as major as it is in the classical world, but it will certainly grow significantly. Yeah, well, that's one of our use cases for NQCC. So optimizing energy grids is a highly non-trivial matter, if you know anything about the business. So if you can do it more efficiently, which means use the same resources but do it more quickly, with a quantum computer, there's an advantage. Now, I should say, of course, that we don't have quantum computers yet of sufficient power to do that problem. Roughly where we are now, we probably we will reach probably 1,000 physical qubits, that is 1,000 quantum switches or 1,000 quantum transistors in the next year or two. We need to provide error correction sitting on top of that. That's also being developed at pace. So my guess is around 2030, we'll have extremely commercially significant error-corrected quantum computers running in many labs around the world. In particular, you can use them now. NQCC offers cloud access to some of the big quantum computing labs around the world, IBM, Google, AWC, Rigetti, D-Wave, there's a whole bunch. And we have an outreach program to all university academics where they can apply for 3 months' time on cloud access to these machines to try out ideas. And they're not quite at the level where you'll be discovering new science, but they will be within a year or two. So if you have some ideas and you're associated with a university, go to our website and apply. Yes, absolutely. A lot of people are thinking about that. One of my colleagues back in Australia at Macquarie University is involved in thinking about how quantum algorithms can be used to improve blockchain encryption. I mean, there are lots of cryptocurrencies that don't necessarily use the same proof of work stuff that Bitcoin does. Ethereum was recently part of a major paper on the archive assessing how quantum computers could be used to improve their particular protocol for crypto. So yeah, that's a major area of application right now. Over here. Oh, there. Okay. Yeah. Oh, that's an interesting idea. Okay, firstly, not all quantum computers need to be cold. The advantage of optical quantum computers is they work at room temperature. Many ion trap quantum computers work at room temperature. Now, the reason that optical quantum computers work at room temperature is because the energy of a visible photon is vastly above the energy of the thermal microwave background. To a photon at optical frequencies, the world looks at absolute zero. And this is why almost all the fundamental tests of quantum entanglement have been done with photons for precisely that reason. So there are quantum technologies like superconducting devices that do require very, very cold temperatures in a dilution fridge. So now you have to ask, what is the cost to do the cooling? And that has to go into the budget. It's pretty substantial. There's another technology based on trapping atoms in optical lattices where you can also cool them down, but now you don't need a fridge because it turns out the thermodynamics of a laser has extremely low entropy, and so it can be used to cool atoms, trapped atoms, very, very efficiently with something, a process called optical pumping. And you're trading off the very low entropy of the laser, very high free energy available coming out of the laser to do the cooling for you. So by no means do all quantum computers require low temperatures. But the superconducting ones are being developed by Google and IBM, and they really are thinking of having thousands of dilution fridges in warehouses like data centers, which clearly is going to cost a lot of money. But yeah, your idea of putting them in space, maybe we should talk to Elon Musk about that. That sounds like something he would be interested in. Oh, are they? Oh, okay, there you go. Yeah, well, I'm not surprised they didn't, miss an opportunity to make some money. Ah, That is an extremely, extremely important question. So first of all, in the setting of a quantum computer, how do you know you're actually dealing with a quantum computer? That is the first problem. So if you're sitting there at your terminal sending signals off to the cloud of some purported quantum computer that you're paying a fortune for, how do you know that it's actually quantum? Well, you can't check it by simulating it classically. That's the whole point. You can't, well, I'll just quickly go here on my laptop and check to see if we did the right thing, because the quantum computer is doing it much faster. So my colleagues at the Quantum Software Lab in Edinburgh have developed protocols to verify a quantum computer is doing something quantum. And it does it pretty much the way we learned in quantum mechanics. We know the world is deeply quantum in a very complex way, but we figured out ways of just doing a little bit of quantum here and there to extract a great deal more quantum from the world. So the way these verification algorithms work, you have a really, really simple quantum computer to interrogate a much bigger quantum computer and reliably prove that it is indeed a quantum computer. It's a little bit like zero knowledge proofs. Now, your other question is in the context of experiment. Well, at the end of the day, even in theoretical physics, we do all these beautiful calculations, but at the end of the day, we have to go and do the experiment and see if it comes out the way the theory predicts. So the same thing will happen in the automated laboratory. All this stuff will be going on, and some new material will pop out, and you'll put pass a current through it and discover that at room temperature it's superconducting. There'll be an absolute crystal clear signature. So you have to actually go and do the experiments after the thing has developed the technology. Okay, so yeah, so let's one of the applications of drug discovery is discover how drugs bind to different proteins. Oh, between different drugs in a prescribing. Oh, that's an extremely important problem. Okay, in fact, I have a master's student at the University of Sussex working on that right now. And so you can have situations where some patient may have, say, 7 problems, and for each problem, there's a different number of drug choices you can use. But you discover that there are pairwise conflicts, and even worse, 3-wise conflicts, and keeping track of all that is incredibly difficult. It turns out to be very closely related to a problem in mathematics called Boolean satisfiability. So you can think of, okay, these are so-called one-hot algorithms, where you only prescribe one drug for each problem, but you don't want conflicts. It's a little bit like saying, I can have X or Y and not B and C. So you can construct a Boolean statement, and quantum computers are getting very good at finding satisfiability clauses for those things. It's also closely related to a problem in genetics, where you have a whole bunch of genes with different alleles, and you're trying to find which mutations would cause difficulties. So yeah. Yeah, so what would be nice is to put an automatic laboratory on the front end of that to provide the data to the actual classical machine learning. That's the idea. Not that you'll notice. All your encryption will change, but you won't know. But okay, it's already out of the labs that there are oodles of quantum startups making lots of money. They're not making profits, but they are selling products because it's too early yet. So yeah, it's already well and truly out of the lab. In fact, we have trouble hiring postdocs at NQCC because it's far more likely a graduating PhD student will get a job in a startup because they pay much more than we can pay. Sorry? What kind of products? Oh, well, there are some selling quantum computing. So there's an optical quantum computing company in the Netherlands called Fix, which just sold a universal optical quantum computer to the German government. Not entirely sure what they're using it for. Maybe they won't tell us. But yeah, that was just last week. And Rigetti and Inflection are selling quantum computers. In fact, I think a company based out of Harvard called QEra sold a big machine to the Japanese government a month or so ago. But of course, they've got a long way from profitability, but they're not selling things. You had a question? Oh, yeah, it's never too late to learn some physics or some mathematics or some science. Yeah, that is absolutely true. It's wide open. We're only just beginning to understand how to control the quantum world. And let me add at this point a cautionary note. We know, at least we're pretty sure, at some point quantum mechanics will fail, because despite a century of trying, we've never been able to get Einstein's theory of general relativity to talk to quantum mechanics and vice versa. So something is missing in the picture. And so clearly, this is one obvious example where there's incredible new science to be discovered. And we know there's a problem, we just don't know what to do with it. So there are incredible opportunities. So anybody who studies maths and physics, chemistry and biology, computer science is going to be in a perfect position to move into these, move into a university lab, but increasingly a corporate lab where the research is being done. Okay, so when you run a quantum computer, there are binary digits in and binary digits out. So the number of digits is no different to what is happening in a classical computer. So the storage problem is just the same. The magic is how the strings are being manipulated in the box. And I know some people sometimes try to explain this by saying, well, it's doing an exponential number of calculations in parallel. That is nonsense. That's not what it's doing. That's how we describe it. What's going on is there are individual quantum devices moving through their quantum states, but when we read it out, we get n bits. At no point in there is a particle in two places at the same time. The people at CERN know only too well. They only detect particles at the particle detectors, nowhere else. And so that's another sort of myth you hear. I can't blame physicists for saying this because it's so hard to explain what's going on in the quantum world. But when you hear them say the particle is in two places at the same time, they've run off the rails. That's not what's happening. What's going on there is equivocation. They're using the word particle in two completely different senses and making the confusion even bigger. So in coming back to the storage question, a quantum computer doesn't need the storage requirements are no bigger than it would be for a classical.
Yeah. So I find that the hardware roadmap are very precise. At the end of the next year, quantum does, Microsoft probably does. And they are absolutely fascinating machines. But I always find that the application for some kind of software, in the sense that I keep asking, what do you think is really the killer application that in 5 years we feel comfortable to justify what we've done? And people might answer cryptography, but solution. Others answer materials of chemistry. Take it. Maybe there is machine learning, but we have already too much machine learning already. So what would be your take on killer application?
Okay, I'm not sure there is a killer app. I think there'll be thousands of extremely profitable applications. One of our jobs at NQCC is to identify use cases right now that when quantum computers in the next 2 or 3 years are big enough will provide a financial advantage. And I'm endlessly surprised by the novel cases that come up. One was finding the optimal way of packing cargo into planes so that when you pack it all in, it's not sort of all heavy on one side and plane sort of flying at an angle the whole time and wasting lots of fuel. You can't sort of stuck it all in and say, oh, that's no good, let's take it all out and try another way. You really need to be able to do it in simulation first. And there's a good quantum algorithm for doing that. And I think it's wide open to people to think of new use cases, and we'll only come up with new use cases by actually using the machines we've got now to see what they can and can't do and generate new ideas for new applications. The killer apps will be in finance. I do think quantum chemistry is going to be an important one, but for that, we're going to need these automated laboratories to get real world data. Designing new drugs and new molecules. These will all be important applications. After all, one of the paths to quantum computing was Richard Feynman's question, which is, why is it so hard to simulate quantum systems on a classical computer? It's really hard. The problems do not scale well. Trying to simulate a simple molecule like caffeine is already very difficult. And Feynman then said, well, okay, well, let's build a quantum device to do the simulations. And that was back in the 80s. And that was one of the paths that led to where we are now. So the killer apps, I don't know. There will be many. And it's up to each and every one of you to think of good applications and put them into practice. The one I mentioned before of drug prescribing to avoid conflicts is, I think, a very important one.
Can I suggest that we'd like to come up and talk to Gerard afterwards? Now would be a great time, and we'll close the formal question asking.
Okay, thanks.